Welcome back to topic 42 for Algebra 2, Graphing Rational Functions. In part 2, we're going to look at some examples on how to identify both the vertical and horizontal asymptote as well as holes in the graph. Let's dive into some examples. What are the asymptotes to the function y equals -3 divided by x? Now remember, asymptotes include both vertical and horizontal. I like to personally think about the vertical asymptotes first because all I need to do is look at the denominator. So if I look at the denominator, here I just have x. Now for a vertical asymptote, we want the denominator to equal 0. So what can I plug in for x in order to make the denominator equivalent to 0? Well, I can have x equals 0. For the horizontal asymptote, that's where we have to look at 3 different cases, comparing the degree of the numerator to the degree of the denominator. But I personally don't see a degree in the numerator. Well, it's there, it's just not written in this case. In the degree of the denominator, we know that this is x to the first power. However, in the numerator, we don't have a variable. That's because it's x to the 0th power. Now, anything to the 0th power just simplifies to 1. So we're left with -3 times 1, or just -3 in our numerator. Since the degree of 0 is less than the degree of 1, we know that our horizontal asymptote will be y equals 0. And that's because as x gets bigger and bigger and bigger, our fraction will become smaller and smaller and smaller and get closer and closer to 0. Looking at the second example, what are the asymptotes to y equals 1 divided by x minus 3? Again, let's start with the vertical asymptote. Looking at the denominator, what can we plug in for x in order to make the denominator equal to 0? Well, if we plug in +3 for x, that will become 3 minus 3, or 0 in the denominator. We can also set the denominator equivalent to 0 and solve for x. So our vertical asymptote is going to be x equals 3. For the horizontal asymptote, again here we notice that we don't have a variable in the numerator. So this is really x to the 0th power. Because 0 is again less than 1, we know as x gets bigger and bigger and bigger, our fraction will get smaller and smaller and approach 0. So our horizontal asymptote is at y equals 0. Moving on to example number 3, which are the asymptotes to the function y equals x minus 3. Now here, I notice that there isn't a denominator of our fraction. However, if I don't see a denominator, there's automatically a 1 there. This is an example of a linear equation. We would be able to graph this. If I look at the denominator in order to determine my vertical asymptote, I know that 1 already does not equal 0. So I do not have a vertical asymptote. For my horizontal asymptote, the degree of the numerator is 1. The degree of the denominator is x to the 0th power. Since 1 is greater than 0, I know that I have no horizontal asymptote. So altogether, I have no asymptotes in this example. For example number 4, which are the asymptotes to the function y equals 1 divided by x minus 3 plus 2? Now this example is really similar to example 2 that we saw on the last slide. If I think about the vertical asymptote, again, I just want to look at my denominator here. What can I plug in for x in order to make the denominator equivalent to 0? I can plug in x equals 3. Now for the horizontal asymptote, Notice how I have 1 divided by x minus 3. Then I also have this plus 2 on the outside. This is a vertical translation. So the graph that we had in example number 2 would be shifted up 2 units. With my horizontal asymptote, the degree of the numerator is 0, and the degree of the denominator is 1. Since 0 is less than 1, this entire value will become closer and closer and closer to 0. But then we still have that vertical translation of adding 2. 0 plus 2 gets us 2, and since our variable that we're dealing with is y, our horizontal asymptote will be at y equals 2. Looking at example number 5, which are the asymptotes to the function y equals 1 divided by x minus 3 plus 3. So again, this example is really similar to number 4. If we look at our denominator for the vertical asymptote, we can plug in x equals 3. For the horizontal asymptote, we have x to the 0th power, which is really in our numerator, x to the 1st power in our denominator. So since the degree of the numerator is less than the degree of the denominator, this entire fraction will become closer and closer and closer to 0 as x gets bigger and bigger. But then we still have this vertical translation of 3. If we add them together, we get our new equation of y equals 3, which is our horizontal asymptote. Example number 6. Which are the asymptotes to the function y equals 3x minus 1 divided by x plus 4? For my vertical asymptote, I'm going to look at my denominator. What can I plug in for x to make it equivalent to 0? Well, since x plus 4 equals 0, I can subtract 4 from both sides and get x equals negative 4. That is my vertical asymptote. The horizontal asymptote, I notice that I have a degree of 1 in the numerator and a degree of 1 in the denominator. So, the degree of the numerator is equal to the degree of the denominator. For my horizontal asymptote, I want to take the leading coefficient of this highest power in the numerator and divide it by the leading coefficient of the highest power in the denominator. So I'm left with y equals 3 divided by 1, since it was 3x in the numerator and really 1x in the denominator. This simplifies to just 3. So my horizontal asymptote is at y equals 3. Okay, now let's move on to example number 7. Example number 7 has a little bit more to it. We want to identify the horizontal asymptotes, the vertical asymptotes, and the holes in the function of x cubed plus x squared divided by x cubed minus 4x squared plus 4x. Then we want to graph them. I don't want us to graph the actual function, but just the asymptotes and the hole. We will get more into graphing the actual rational function in part 3. What I like to first start off with is identifying the holes in the function. This will come in handy when I need to determine what my vertical asymptote is later on. So first, I'm going to identify the hole. Looking at my function, I want to factor the numerator and denominator so that I can identify a common factor in both my numerator and denominator. In both the numerator and denominator, I can factor out an x. And in the numerator, I'm left with x squared plus x. And if I factor out an x in the denominator, I'm left with x squared minus 4x plus 4. Now, could I factor this function even further? Yes. However, the only common factor that they both share is x. Now, according to part 1, I'm going to take this factor that I just reduced and set it equal to 0 to solve for what my x value would be. So my factor of x set equal to 0 means my x-coordinate is just simply going to be 0. Sometimes you might deal with a binomial and then you'll have to solve for x. This one was pretty straightforward. Now, a hole in the graph is a specific point on your curve, on one of the branches. However, I can't just use x equals 0. I need a y-coordinate. So, what I have to do now is I have to plug my x value back in, but not into the original equation, but into this new reduced equation. That's because if I plugged it back into the original equation, I would see that it would be undefined in the denominator. Because again, if I plug in 0 in for x, it would be 0 times this entire quantity of 0 squared minus 4 times 0 plus 4, and I would get 0 in the denominator. That's undefined. That's exactly why we have a hole. It doesn't make sense in the graph, so there is a legit hole in the graph. So what I'm going to do is I'm going to plug in 0 into this new function. So I'm going to have 0 squared plus 0 over 0 squared minus 4 times 0 plus 4. And this is to find the y-coordinate, because this entire expression is equal to y. Simplifying, I'm left with 0 squared plus 0 gives me 0 in the numerator, and then 0 squared minus 4 times 0 plus 4 gets me 4 in the denominator. 0 divided by 4 gets me 0. So the coordinate of my hole is going to be at 0, 0. And in my graph, I'm literally going to draw a hole or an open circle at that point. Now what I like to do is I like to look at the vertical asymptote. With the vertical asymptote, remember, I only need to look at the denominator. So I have x cubed minus 4x squared plus 4x, and I'm going to factor it. I've known from part 1 of this problem that I can factor an x, and I'm left with x squared minus 4x plus 4. I can factor this following trinomial even further to get x times x minus 2 times x minus 2, or x minus 2 squared. If I were to set this equal to 0, I know that my values of x could either be 0 or positive 2. However, because we had this removable discontinuity with the hole, literally we were removing x from our function, x equals 0 cannot be a vertical asymptote. There's already a hole in the graph there. So the only vertical asymptote that I can have is at x equals 2. So I'm going to graph that. Since x equals 2 is a vertical line, I'm going to find 2 and draw a vertical line straight through it. And remember, with asymptotes, we draw those with dashed lines. Last but not least, we're going to go into our horizontal asymptote. Remember, horizontal asymptote, we need to compare the degree of the numerator with the degree of the denominator. Looking at my original function, I have x cubed and x cubed. Those are the highest powers. Also, these highest powers are equal, so the degree of the numerator is equal to the degree of the denominator. So all I need to do is take those leading coefficients and divide them. In the numerator, there's a 1 here. In the denominator, there's also a 1. So my horizontal asymptote is going to be 1 divided by 1, or just y equals 1. I can graph this since it's a horizontal asymptote. At y equals 1, it's going to be a horizontal dashed line. And there are the asymptotes as well as the holes in the graph. Thank you for watching part 2 of topic 42 for Algebra 2, Graphing Rational Functions.